the fourth dimension. Now, to approach that, let's consider a cube. We can imagine a cube in the following way. You take a line segment and move it at right angles to itself in equal length. That makes a square. Move that square in equal length at right angles to itself, and you have a cube. Now, this cube, we understand, casts a shadow. And that shadow we recognize. It's, ordinarily drawn in third grade classrooms as two squares with their vertices connected. Now, if we look at the shadow of a three-dimensional object in two dimensions, we see that, in this case, not all the lines appear equal. Not all the angles are right angles. The three-dimensional object has not been perfectly represented in its projection in two dimensions, but that's part of the cost of losing a dimension in the projection. Now, let's take this three-dimensional cube and project it, carry it through a fourth. Now, let's take this three-dimensional cube and project it, carry it through a fourth physical dimension. Not that way, not that way, not that way, but at right angles to those three directions. I can't show you what direction that is, but imagine that there is a fourth physical dimension. In that case, we would generate a four-dimensional hypercube, which is also called a tesseract. I cannot show you a tesseract because I and you are trapped in three dimensions. But what I can show you is the shadow in three dimensions of a four-dimensional hypercube or tesseract. This is it. And you can see it's two nested cubes, all the vertices connected by lines. And now the real tesseract in four dimensions would have all the lines of equal length and all the angles right angles. That's not what we see here, but that's the penalty of projection.